Welcome to the PinPoint Diagnostic class. This class will focus on rate control with the envelope controller and the different operation modes we have in order to do that. The first thing that we'll do is we'll come over to the in-command display here and we'll take a look at the different operational modes for rate control. To do that, we're going to come into the wrench. We're going to go to the initial setup. In the initial setup, we're going to go to configuration. And when we want to change the way that it does rate control, we look at item number 2 here, which is the fluid control mode. So right now it is set to conventional spray control mode. So conventional spray control mode is just operates just like a traditional sprayer would, where it uses a flow meter to read the amount of flow coming through the machine, and then it uses a PWM valve or an electric motorized valve to increase and decrease the flow coming out through the boom. So as you speed up, your pressure would increase. As you slow down, your pressure would decrease. And it would all be based off of the control valve or the PWM pump and the flow meter. So the conventional mode works exactly like you would think that the conventional mode should work on a standard machine. The standard operating configuration for the envelope controller is Synchro mode. So in Synchro mode, we control both the pressure and the flow at the same time. So in Synchro mode, the envelope controller will pulse the solenoid valves in order to control the flow, so it'll increase and decrease the duty cycle of those valves. As you speed up, the duty cycle would increase to allow more flow to come through, or as you slow down, the duty cycle of the PWM solenoid valves would decrease to allow less flow to come through. So we would control the flow through the solenoids by pulsing them, and then we would use either your PWM pump or your electric regulating valve, your motorized valve, to increase or decrease the pressure to maintain a constant pressure within the system. So this is a traditional PWM operation type mode. And the last mode that we would be interested in looking at in here is the no pulse mode. So with the envelope controller, there may be situations where you want your individual nozzle control, you want your solenoid nozzle controllers to turn on and off on the boom, either as sections or individual nozzles, depending on your task controller's capability. But you don't want them to pulse. You want a conventional style application where you have a constant fan or a constant stream with no nozzle pulsing. So we call that no pulse mode, where it works just like a conventional sprayer, except the flow comes through your solenoids, and the solenoids turn on and off just like they would in PWM mode. The only difference here is in no pulse mode, the solenoid valves would just turn on and off like an electronic diaphragm drip check at every nozzle position. So now that we've familiarized ourselves with the 3 different rate control operation modes of our envelope controller, we can dig into each one of these modes and exactly how it operates on the machine and what we need to do diagnostically to troubleshoot these circuits. In this portion of the training, we're going to talk about conventional rate control with your envelope controller. So the first thing that we're going to do is go take a look at our in-command or our VT screen and in the in-command display. And from here, we're going to go to the wrench. We're going to go into initial setup. And initial setup, we'll go to configuration. We want to make sure our fluid control mode is set to conventional. For this diagnostic purpose, it could be set to no pulse mode or conventional mode, either one. From a diagnostic perspective, they operate exactly the same. The only difference between these 2 modes is in no pulse mode, our solenoid valves turn on and off as the section controllers. In conventional mode, ball valves turn sections on and off for the sectional control. So conventional mode or no pulse mode, we can select either one of those modes diagnostically. They're going to behave the same. So we come back out to our run screen. We have it set to conventional mode now. The second step in this process is going to be what pins or how do we need to troubleshoot this. So we'll come to our operator's manual. Within the operator's manual, we'll scroll down to the very bottom of the operator's manual. And from there, we have a schematic of the PinPoint hub, which we've seen in prior trainings. And in here, we're going to focus on this port number 1 up here at the top. and we're going to look at 2 pins within that port. That is pins 2 and 5, servo out increase and servo out decrease. And these 2 pins right here, 2 and 5, are what's going to be tied into your PWM pump or your electric motorized valve to increase or decrease the amount of flow coming out of the boom when you're in conventional rate control. So once we have that all set up, we can come over to our in-command view, and the operation is going to be really simple. One of the things that you're going to notice right away is that within this pressure, we have nothing that we can select here, and that's because in conventional mode or no pulse mode, we're not actually controlling the pressure. The pressure is controlled as you increase and decrease your speed by your tip size, just as a conventional sprayer would operate. So within this, I have a self-test speed set in here of 10 miles per hour. The system is set to off right now. I have a number 4 nozzle programmed in here. And in the environment we're in right now, we're using simulators, so I don't have a flow meter hooked up to this right now. But in a conventional, normal environment, it would be hooked into a flow meter, and the flow meter would be reporting flow back to the controller. Since we don't have a flow meter, the envelope automatically goes over and uses tip size, pressure, and speed to calculate what the flow would be. So you do have a way to operate even if you didn't have a flow meter on the machine. And over here in this gallon per acre, I'm just going to select a rate 1 of 10 gallons per acre. You could use the RX for your task control rate if you were wanting to use the rate driven from a task controller. I'm going to use the internal rate control for this example, so R1 10 gallons per acre. Now when I come in here to the system and I turn my boom into the on position, you're going to see that all of the nozzles turn on and we're at 100% duty cycle, or the valves are on or locked open, or if you have ball valves on the machine, they're on and open, and we are now spraying. So you can see that at target rate of 10 gallons per acre, 10 miles per hour, and 30 psi with a number 4 tip, we're on target rate. Now I have a pressure simulator on here, so one of the things that we can see is that if I decrease my pressure, in other words, this could be slowing down, you can see that the target rate actually goes down. And that's because we're in a conventional mode now, so your pressure is dictated by your rate and your speed. Same thing, if I come over here and my pressure goes up, now I'm at 40 psi, you can see that if my speed stayed constant, I'm actually over my target rate. So I'm going to set my pressure back down to 30 psi here, and you can see now we're back on 10 gallons per acre. The same exact thing happens if I were to change my sprayer speed. So if I slowed down to 8 miles per hour, let's say, you can see now I'm over applying. But on my sprayer, what would actually happen now is the envelope controller would start decreasing the pressure until we got down back on our target rate. So you can now see 8 miles per hour, 10 gallons per acre, and 19 to 20 psi, we would be on target rate. The same thing would happen if we increased our sprayer speed to, let's say, 12 miles per hour. You can see now I'm way under my target rate, so the envelope would start sending a signal to the pump or electric valve to increase the pressure so that we could get back on target rate. And you can now see when I get up here around 40 psi, I'm now back on my target rate. So the envelope controller works just exactly like a conventional sprayer you would expect it to. As you slow down, the pressure goes down. As you speed up, the pressure goes up in order to maintain a fixed target rate. Now, if we want to come and look at this from a what's going on the machine or a diagnostic perspective, right now we have the voltmeter tied into pins 2 and 5 on the servo port. Now you could tie into pins 2 and 5 physically at the gateway hub. You could tie into it where the gateway hub goes into the chassis harness, or you could measure this signal right at the connection, typically a 2-pin DT connector at the pump. So right now we have the voltmeter set to measure volts, and we're at 10 gallons per acre, 12 miles per hour. So what you're going to see now is if I lower my pressure to 30 psi, you can see now the voltage is starting to increase. We're now at 10 volts instead of 9 volts, and that is because it's increasing the voltage or the signal to the pump to try and create more flow in order to get this rate on target. The same thing would happen if I decrease my pressure, say to 15 psi. Now I'm under target. I'm sorry, I need to go in the other direction. If I were to increase my pressure up to 60 psi, you can see now that the voltage is falling and it's trying to decrease the flow coming out of the pump, and it's going to continue to keep decreasing that voltage, trying to get this on target rate. You can see we're all the way down to 5.7 volts now, 5.2, and it's just going to take that voltage all the way down to our minimum threshold in order to try and get that rate to come down. Now we're in a simulated pressure environment, so the only way it's going to come down is if I come over here and I actually decrease that pressure myself. So now again, I'll show going below the target. So now it needs to increase that voltage. You can see that voltage starting to come up on that pump. Now, a better way to look at this is maybe as a percentage, which is the way we program most of our controllers. So I'm going to change my voltmeter over to look at the frequency or the duty cycle that we're sending the pump instead of the voltage. So I'm going to switch that over. So right now you can see that we're at 7.8 gallons per acre. It's trying to get to our target of 10 gallons per acre, and it's low, or the pressure is low. So it's sending 78% duty cycle to the pump, or the maximum programmed duty cycle it can send to try and achieve target rate, but we're under rate. So now I'm going to start increasing the pressure again. So we are on our target right now, so it's not controlling. But what would happen is if my pressure came above the target back up here to this 60 psi, you'll now see that the pump PWM is now falling, 63 now, 60. It's going to keep on decreasing the pump duty cycle now to try and decrease this pressure so that it can get on target rate. And it's going to continue to do that until we fall back down into our 40 psi range, and then it's going to stop the active control. Now you can see before I got there, it got down to 28% duty cycle, which is where we're at right now. So what you see is at the very low end, now it's ramping it up a little bit until I get back on 40 psi, and now you'll see it stabilize. So what we see is that it went from 28% minimum duty cycle to a maximum of 78% duty cycle. And if we come in here and look at this envelope controller in this pressure menu in the pump setup, we set our servo minimum to 28%. So that means whenever the rate was too high and it was trying to bring it down, it'll only allow it to come down to a minimum of 28%. We set a servo maximum of 78%. So when the rate was too low and it was trying to increase the flow through that pump, it would only drive it to a maximum of 78%. So not only can we see how the voltage should be reading and behaving at the pump connection, we can see that the values that we program in here actually dictate the minimum and the maximum thresholds that go to the pump while we're driving it. So again, from a rate control perspective, this works exactly the same in no pulse mode or conventional mode. We can tie into that pump signal. We can see it increase and decrease by voltage or percent duty cycle to try and achieve the target rate in a conventional application method. In this segment, we'll discuss diagnostics for PWM rate control. And in order to do that, we're going to come back over to our in-command VT view, and within the envelope VT, we're going to come into our wrench. We're going to go into our initial setup. From the initial setup, we go to configuration, and in there, our fluid control mode is going to be synchro. or this is PWM valve control mode, and this is where we're going to be pulsing the solenoid valves to control the flow rate, and we're also going to be driving the pump to control the pressure. So we control both the flow rate and the pressure at the same time, so we maintain a constant pressure over a wide speed range. When we come back out here to our home, again, just as we did in the previous sessions, we have a self-test speed in here of 10 miles per hour. I'm using the internal rate control. I have a target rate of 10 gallons per acre. I have a pressure simulator hooked up. I don't have a flow meter, so I'm not actually live spraying at this point. But I have my pressure emulator set to 40 psi. So when I come in here and turn my system to my boom to on, we can see now that the boom turns on. Now I do have a profile set up with the middle boom section turned on. That's boom section has pulsing valves connected to it so that we don't have to hear them. I just have those turned off. But if I select profile 1, they would turn on. I'm going to select our boom 2 profile, which leaves that section off. So in PWM rate control mode, we have our pressure control right here, and it's going to operate. If you watch the pressure diagnostic class, or you want to know how to troubleshoot or diagnose this pressure control circuit, all you have to do is go to that pressure control class. All the diagnostics and what pins to look at and how to test those are all listed in that class. It's going to operate it just like a traditional PWM valve. Whenever the target pressure gets lower, it's going to increase the PWM to increase the pressure and achieve the target pressure. When the pressure gets too high, it's going to decrease the pump PWM to try and lower that pressure so that we maintain our target pressure at all times. Same thing, different concept with an electric motorized valve. It's going to turn that motorized valve to regulate the flow, therefore the pressure that's coming through the boom. So again, if you want to look at how to hook up and test the pressure control side of that, go to the pressure control classes where that's available. Now on the rate control side of this, there's really a couple different parameters, 3 different parameters in fact, that we have to look at to maintain our target rate. One of them is as our target rate changes, it's going to change the duty cycle of the valves. So an example of this is, I'm actually going to change this field right here, this GPA, to duty cycle, so we can look and see what's happening to the duty cycle of the valves. So I'm going to go on and set this boom to off. I'm going to go to the wrench. I'm going to go to flow and display rate or duty cycle. Right here, I can select that I want to see duty cycle on my run screen. Now you can see that this field over here has now changed from gallons per acre to duty cycle. So now when I turn this boom on, it's going to be reporting to us what the duty cycle of the nozzles is at this point in time. So right now we're at rate 1 of 10 gallons per acre, and it's at 58% duty cycle. So if I change to my rate 2 of 15 gallons per acre, you can see right there our duty cycle jumps up to 87%. So when the target rate increased, it increased the duty cycle of those solenoid valves so that more flow could come through them in order to achieve that target rate. And if I come back down here to my rate 1, my 10 gallons per acre, you can see in order to achieve that target rate, it just bumps that duty cycle of the solenoids down. Same thing if we come over here and we look at speed. If I change my speed to 5 miles per hour, now you can see that in order to be on target rate of our, again, still 10 gallons per acre, it had to lower the duty cycle to 30% to be on target rate. So lower speed means we need less flow means we need a lower duty cycle. Same thing if I had gone from 5 to, let's say, 15 miles per hour, you can see now my duty cycle jumps up. I'm at almost 90% duty cycle now. So I tripled my speed. My duty cycle went to close to 90% to still be maintaining that target rate. Now, something that could also happen is that, let's say I was at 15 miles per hour and I selected my rate 2 here. Well, you can see that I'm at 100% duty cycle. Now, what you can't see up here is the actual rate that I'm on. So I'm going to turn that to off real quick. I'm going to come back out here to flow. I'm going to set that view back to rate. And now if I turn my boom back to on, you can see that whenever I have my target rate set at 15 and I'm going 15 miles per hour, I'm actually under applying. I'm only putting out 11.4 gallons per acre right now. And that's because my solenoids are at 100% duty cycle, or they're wide open. They're not pulsing right now. They're putting out all of the flow that they possibly can. So in this situation where you're driving to a speed where the solenoids hit 100% duty cycle and your rate starts falling off, that means a couple different things. That means you could try running at a higher pressure in order to get more flow out. You could try putting in a bigger nozzle size in order to get more flow out. Otherwise, you're just going to have to decrease your speed to get onto your target rate. So I can put that back to, say, 12 miles per hour now. You can see I'm now on my target rate. I'm still at 100% duty cycle, so this is right on the edge of what it can do at that for this tip size. So again, I come back down to 10 miles per hour, and we're going to be back in a more acceptable range for that tip. So again, that's using changing our rate, and we can see what the effect is on the duty cycle. We also changed our speed to see what the effect was on duty cycle, or if we increase our rate or we increase our speed, we're going to see an increase in duty cycle or the demand for flow. If we decrease our rate or we decrease our duty cycle, or decrease our rate or our speed, we're going to see a decrease in nozzle duty cycle. In other words, it needs less flow, so it's going to turn that duty cycle down. Now, there is another relationship, and that is pressure. So as our pressure increases, we get more flow through a nozzle. So if our target pressure goes up, we would actually decrease the duty cycle in order to maintain that target rate that we're looking for. So I'm at 40 PSI right now. If I were to change my actual boom pressure to 60 PSI, and it's going red just because my target's 40. I'm using a pressure emulator. But you can see now that my duty cycle has actually fallen off, and I'm going to switch this quickly back over into displaying duty cycle for us. Turn that boom back on. So now we're at 48% duty cycle. So you can see as my pressure goes up, my duty cycle goes down. So it's an inverse relationship to what the rate and the speed did. When rate and speed went up, duty cycle went up. When rate and speed went down, duty cycle went down. However, as pressure increases, my duty cycle is going to decrease. And that's because there's more pressure to provide flow across the nozzle. And as my pressure decreases, my duty cycle is going to increase. And you can see we can go all the way down to 20, and as our pressure lower, our duty cycle gets much higher. So as we change our pressure, it changes the duty cycle range that we'll be using on that nozzle just because of the force that we have to get the actual flow through the nozzle. And the last parameter that we use to look at diagnostically how our PWM rate control is working is our nozzle size down here. So right now I have a number 6 nozzle in there, and I'm going to put my pressure back up here to around 40 PSI. And so I have a number 6 nozzle in there right now. So just like increasing your pressure, when you change your tip sizes, it also changes the duty cycle. So if I go from a number 6 to a number 8 tip, it doesn't take as much pressure to get the same flow rate through that nozzle because I'm using a bigger nozzle than I was. So now if I change that 6 to an 8 nozzle, you can see that duty cycle jump down. If I change it to a number 10 nozzle, that duty cycle continues to fall as I continue to increase this nozzle size until I get all the way back down to a number 3 nozzle. Now I'm at a smaller nozzle, which means it can't get as much flow through there, so the duty cycle goes up. So I have to, make sure that I'm operating within the correct nozzle size for the application that I'm doing. And so this is how your PWM control works. We use the pressure control circuit to just set the pump at a fixed pressure and then regulate to that pressure using a PWM pump or a regulating valve. And then we use the duty cycle of the nozzles to control the flow rate. So again, as you speed up or slow down, increase or decrease your rate, that duty cycle is going to change. And as you change your nozzle sizes and your pressure, it's going to change the way that duty cycle behaves. So we have to manage all of these things, and this is why it's so important to do proper nozzle selection, which we'll get into in some other diagnostic classes, in order to operate your PWM nozzle control system effectively.